All right. Okay, real quick review. In a series circuit, what measurement is the same? Current is the same. With parallel, what measurement is the same? Voltage. Okay. So I'm just gonna throw this up here just because you know you're gonna use it a lot. Thumbs up when you have a guess. Have a conversation.
There's seven. So one thing says it's the 1 over R.
Okay.
So that must have been the 7, so 730.
I'll,
The other.
I'll give you that one.
Mr. Smiley. Mr. Smiley. Wait,
Hi.
hey, what's up? How are you doing? What is it,
Well.
1 over R?
Parallel.
What is 1 over R?
But that's not what you want to employ here.
Okay. And the other one was 737. Apple. Yeah. Which I know is late.
We're gonna call that one a loss on that one. Okay, correct answer is A. Is everybody good with that? You got 12 volts here, 12 volts here. Independently hooked up, voltage gain equals voltage drop. So 12 volts across each one of those. Okay, good. 6 amps, 4 amps. Same circuit. Tell your neighbor. Correct answer is in parallel. Your current is summative, meaning you add them up. We already discerned that there's 6 amps going through this one, 4 amps going through this one. Okay, so there's 4 amps going through here, and there's 6 amps going through here. So the total amount of current coming out of the battery is 10 amps. Good with that? Yep. We had 4 amps going through this guy, 6 amps going through this guy. Both are coming from the battery. So the total amount of current coming out of the battery is the sum of them. 10 amps. Good with that? Next question. Here we go. Here we go. Talk to your neighbor.
I always get scared when like you asking something and I go, like I don't know what it's called. The rate at which no, that's just like from the water towers.
I thought I'd really want.
Sorry, I'm talking about important stuff, okay?
Ladies, this little device right there is like the bane of your. Yeah. That's what your tests say. Correct answer is not C. Correct answer is A. No, listen. I will. Here we go. If you have a bucket and you put holes in the bucket, more holes is going to drain faster than less holes. If you have a container and you pop a hole and then you pop another hole, that's going to drain the combination of those two is going to drain this bucket faster. What happened to the rate at which the water draining from the tower? Okay, fair enough. Okay, fair enough. That's not going to affect how fast the water goes out of this hole. Agreed. Okay, but all together, listen. What I'm going for is how quickly the water level is dropping. How quickly the water level in here is dropping. It's going to drop faster. This water tower is going to be drained faster when there's more holes, when there's more pipes added to it. Good? Okay, here we go. Yes, focus is a little bit struggling today. Correct answer is? Correct answer is? Okay, we're adding another pathway for the water to escape. We're adding another pathway, another resistor, another path for this to go through. So like bringing us back to this question here. We knew that this was 6 amps. This is 10 or 4 amps. So the total coming out is 10 amps. If I added yet another one that had a resistance of, let's make this easy on myself, 6 ohms. That's me 2 amps coming out of there. We're going through this one. So now the total current is going to be 12. You okay with that? Okay, because the total current in parallel, you add them, every branch. You okay with that? They're independently hooked up. Okay, they're just as bright as if there was one light bulb. So there needs to be more current coming out of the battery to be able to light this light bulb, independent from these two. Does that make sense? That's how your light bulbs stayed the same brightness as you plugged them in parallel. Versus in series, they got dimmer. Like, how do they do that? Because they're independently hooked up, and there's now more current coming out of the battery, out of the power supply. You all right with that? Okay, so same scenario, different question. Have a conversation.
So the resistor just goes up if there's more resistors. Well, I don't get if you add stuff to the resistor, then obviously the resistance is going up. Like if you add more to RO, R goes up.
Wait, what do we know about the I think it's that. So after you take one
True, but where does it say
it's
that?
up, then it's down.
How is current going up?
You're more.
Like you just have to know that.
You have more holes in your water tower. I'll give you another analogy. Okay, correct answer by the math says what? Has to be C. Why? I don't know. That's what the math says. Good. Go with the math. I'll tell you conceptually why. But listen, you've got to trust the math. Okay? I will. I'll do it. We'll do a whole story because this is totally counterintuitive. If you're like, I don't get it, you join the line. Okay? Here's why it makes sense conceptually. Let's say that resistors are checkout lines at Walmart. Okay? You're the manager of Walmart. You are trying to get as many people in and out of the store as possible. Okay? Let's say it's Christmas time at Walmart. Craziness. Okay? The resistor, like if a checkout line was a resistor, let's say we added resistors in series. That would mean you'd have to go to 2 checkout lines to get out. That would definitely increase the resistance. You had to go through the line and then you had to go to customer service. Like, oh, this is taking forever. Okay? Is everybody okay with that? If you add another resistor in parallel, that's like adding another checkout line, opening another checkout line at Walmart. Does that help or hinder drain Walmart? It helps. Does that make sense? Regardless of how good or bad the checkout person is, Like you're going to go for you're trying to find the one who's going to get you out fastest as an individual, but as a manager, you're looking at overall. If you open up another checkout line, that's going to help get people out of the Walmart faster. There's more people leaving Walmart per hour with 2 lanes open versus 1. The customers have another choice. They have another path. As you add another resistor in parallel, think of it not so much as adding a resistor, but adding another path, another choice. It can go here, 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 or there. Or reality, you can think of it as, hey, I've got another appliance I got to power. It has the same amount of pressure, so I have to give more current coming out of this to supply this one now, and this one too. Is that how we doing with that? Okay. Think of it as adding not a resistor, but as another option, another path. Okay. So mathematically, here we go. So get out your calculator. Finding the total resistance or equivalent resistance in parallel follows this equation. Okay. So don't do this yet. I'm going to show you a cool button. If you have a calculator that looks like this, or a calculator that's a Casio, you're looking for the x to the -1 button. If you have a calculator like this, you're looking for the 1/x button. You have one of the two. That button's going to be your friend on these problems. Okay. Now, you could do this by hand, but, well, I mean, here's how you do this. Ready? You go 4, this button, plus 6, this button, plus 12, this button, equals 0.5. Make sure everybody gets 0.5. Okay. That is not the answer. Yet. That is equal to 1/R. I want R. Do not stop here prematurely. Very popular pitfall. Okay? You need to find the reciprocal. How do you do that? You just hit this button again.
Oh my goodness.
Craziness. And hit equals. Not kidding you. Straight up. It's awesome. That's what it is. Okay. Does that make sense? What you're doing? Okay. That button just finds the reciprocal. 1/. Okay. So I want to show you math-wise. Let's say we added a 4th resistor of 2 ohms. Do it. Find the total resistance. Super easy. So the reciprocal of 1 is 1. Where was there, which one had less resistance? One with another resistor. Another path. Another line at Walmart. Giving you the option to check out. Good with that? Okay. Get out your calculator and try it. Tell your neighbor. Okay. You should have said A. If you said B, that's because you forgot to find the reciprocal. Okay? Don't do that. Don't forget. Okay? Conceptually, here's how you get the right answer. Ready for this? If you have resistors in parallel, their total resistance will be less than the least resistor. If you have resistors in parallel, the total resistance is going to be less than the smallest resistor. Okay? Lines in Walmart, check out lines. This is like the employee of the year. They're like, this is like your grandma's best friend. Who wants to show you all her pictures of grandkids and like, how's your grandma doing? Like, like super big resistor. But you're hoping you're not in her line. But if you're the manager, she's still helping. Regardless of, it's better that she's there rather than not. Does that make sense? Even if it's super resistive, she's still helping drain the water tower. She's still helping get people out of Walmart faster than if that line wasn't open. Okay? All right. Kirchhoff's junction rule. What goes in has to go out. Hit it discussed it in the video. That's the junction of two wires. Thumbs up when you have a guess. Direction of current is out of positive into negative. What goes in has to come out. Talk to your neighbor.
Actually, maybe this. But it hasn't like gone through this. So maybe it is.
Okay. Let's take this in pieces. Which one's greater? 2 or 3? Has a greater current. She has greater current. 3. Why? Less resistance here. They have the same voltage, so less resistance. So, Kirchhoff's junction rule applied to this scenario says current 1 is equal to the sum, that's the current in this junction, is equal to the current out, which is 2 plus 3, because you got 2 things going out. Correct answer is A. All of the current goes out of the battery, and right here at the junction splits. There's a choice. Some of it goes this way, some of it goes that way. That makes sense? You can kind of think of about like a river forking. It's all coming. Okay? What goes into a junction has to come out of a junction. Thumbs up when you have a guess. Have a conversation.
No, because it has to go that way. 5 is the but also maybe like maybe 5
Everything that goes out.
No, 5 definitely is. But also, I don't know.
Yeah, I don't think they're the same. I feel like no other
Okay, what do you say? Okay. Let me address some things right here. How does 3 compare to 4? Has to be the same because junction rule, whatever comes in has to go out. Okay? There's only one single path after you get this, that there's no possibility for current to be doing anything. Like the amount of water going by this point every second has to equal the amount of water going by that every second. The amount of electrons every second going by this has to equal the same amount of electrons going by every second. It's the same current, same path. There's no other place for the electrons to go. Okay? So 3 and 4 are identical. So this point here, if I made this point 6, 2 and 6 have to be the same. The same branch, the same path. So 4 is going into the junction, 6 is going into the junction, 5 is coming out of the junction. Okay, so this would be 4 plus 6 equals 5. And we know that 4 is equal to 3, and 2 is equal to 6. So 5 and 1 are the same. Conceptually, whatever comes out of the battery has to go back into the battery. Has to. Good with that. Give this one a shot. Thumbs up when you have a guess. Have a conversation.
I think it's big.
Yeah,
Okay. Let's take it in pieces. 1, 2, and 3. Rank those. Just 1, 2, and 3. Which has most? 3, and then 1, and then 2. Because least resistance, middle, most resistance. Okay? They're independent. Now, 4, looking at this junction, is a combination of 3 going in and 2 going in. 4 is coming out. So 4 has to be more than 2 and 3 because it's the combination of this and this. It's like the Tippecanoe River and the Wildcat Creek. Or it's like the Tippecanoe River and the Wabash. Bigger. Okay, once they come together. And then here, 4 goes into this junction and 1 goes into this junction. 5's what comes out, so 5 is the most. You okay with that? Questions? Points of confusion?
So what's the answer?
Correct answer is C. Crazy cats.
Is it emphasis?
Come on.
What?
What you got?
No, I just thought you said that 3 was smaller than the other 2. Than 1 and 2.
You know, it has the least resistance, therefore has the most current. Because they all have the same, it says 12 volts. They have the same voltage. Smaller resistance, more current. Okay. Thumbs up when you have a guess. Have a conversation.
These kids are genius.
Correct answer is? Correct answer is A. Okay. Here we go. Here we go. Ready? All the current goes through here. It goes through 1. Here, we have to provide the same amount of current to 80 and to 70 as you did here, but now you also have to apply, you have to supply current to 90 as well. Get at that? As you add more resistors in parallel, you're adding more paths, and your current's going to go up. Okay, if you turn off your TV, does the rest of your house go out? No. Okay, so simplistic wise, it's wired. You're wired in parallel. Okay, what happens to the total current as you add more resistors in parallel? Total current goes up. What happens when you have a lot of current in a wire? Physically, what happens? It gets hot. Is there any potential hazard to a really hot wire? Fire. You do not want too much current going through your wires in your house. You could have a house fire. And this is why we have what? Circuit breakers or fuses. Okay? Come on back here. Okay. I don't know if you know where your, I hope you do, where your electrical box is in your house. Folks, if you can make sure everybody can see, if you turn around, someone shorter than you is behind you, get in here. Okay. Your electrical box is probably in your basement, your garage, your utility closet, somewhere. It's a big gray box on a wall with a lot of wires sticking out of the top of it. You open it up, you'll see, most of you will see switches. Those are circuit breakers. Back in the day, grandparents' age, they used to have fuses and have a whole bunch of these things. Okay? If you look through the window, there's a green wire connected by a spring. Okay? If you look in there, look in the window, there's a green wire with a spring. Okay? That is designed to be the first place it burns. It gets hot and it breaks. Okay? We still have fuses in cars. They look like colorful buck teeth. Okay? The part that burns is the Z between in the colored part. Okay? You can look at that. Go ahead and pass that around. Ready? Catch. And then other computer components have fuses that kind of look like a pill. Oh, sorry, that's wrong. Okay, so I'm going to create a circuit breaker with some steel wool. Okay. Okay, so what I'm going to do.
But it says it's busted. What comes in must come out.
Okay.
Oh yeah.
So this is going to be our circuit breaker. Okay, this is what you're focused on. So as I turn this on, okay, we got current flowing through this. I'm going to plug another thing up in parallel. Plug in another appliance. Okay. I don't know if you saw the smoke there. I saw some smoke. Hook up another appliance in parallel. Thank you. Do you see the smoke?
No.
See it? You're getting kind of red.
Oh, that's it's angry. No, that's.
Okay, I'm gonna plug up another one. Come on, baby. Come on. You can't see that in there.
Come on, baby. There it is. Give it
There it
oxygen. Oh!
Whoa! Woo! Okay, so all right, so we just blew the fuse. Okay. Nowadays, you don't have to worry about breaking. Like back in the day, you'd have to go to Walmart and get another fuse and stick it in there. Now you can just flip the circuit breaker back. Okay. Now, but before you flip the circuit breaker back, you need to turn off the thing that made it trip in the first place. Okay. Now, a fuse or circuit breaker is wired in series with a bunch of different outlets or appliances in your house. Like if the circuit breaker blows or like trips, it's not just one spot, it's like a whole, like a room or two in your house. Okay, because the circuit breaker is wired in series with all those things, but these are wired in parallel individually. So what appliances tend to cause the circuit breaker to trip more readily, just based on a personal experience? Oh, come on. You've never.
Is it like the ones that have like multiple outlets that you just plug in one big extension?
Yep. That'll definitely do it. Multiple outlets. So,
Extension cord?
Yeah, those are Airbnb cause.
okay. How many people have caused the circuit breaker to trip? What? Really? You guys, interesting. Yeah. Good question. I'll come back to that here in a second. Okay. Here, anything that heats something electrically takes a lot of current. Toaster, hair dryer, space heater, crock pot. What?
Air fryer.
Sure, air fryer. Anything that's causing it to get hot electrically requires a lot of current. Those are usually the culprits for causing a circuit breaker to trip. So if you find yourself tripping a circuit breaker, turn that off, figure out what else went out, flip the circuit breaker back on, turn off some of the appliances that you don't need, and then try your heating device. Does that make sense? Okay. JP, the blackouts or brownouts in cities, that is it's probably because there's something malfunction at the power plant rather than too many people. Now there is, in some developing nations, what they will do is they will have certain sectors where they'll have electricity. You'll have electricity on for like 4 hours of the day. Then they'll turn it off and give another sector on because they can't produce, their generators can't produce enough electricity. So it's not so much the wires, the infrastructure can, the wires can't handle it. It's the generation of power. There's not enough for that. Does that make sense?
Yeah. What
Ben.
about like the outlets in bathrooms that have like the
Beautiful question. So the question was, there's these GF or G, what are those called? GFCIs or something like that, ground fault connector, something or other. Okay, so we don't know yet. You don't know as a class yet the science behind that, but we will. What we do, what that registers, they do this in bathrooms and outside and like things that could get wet. If there's a short, it reads it. It's like, hey, there's more current coming. There's a large amount of current, and so it acts kind of like a little circuit breaker. It works differently. Circuit breakers work off of temperature, so like it gets too hot, it measures temperature. Those measure current, but it has the same function. So you just like reset. Sound good? Okay. Have a seat. Remember your homework.